This is an example using the conditional disjunction equivalence rule. The example is presented symbolically only, without a story. Feel free to devise your own story to fit it. The premises that we will be considering in this problem are Q or P together with not P and the negation of the conjunction of Q and S. The conclusion we seek is S implies R. How should we construct a proof of this? As we often do, we will try to argue backwards from the conclusion. The conclusion is S implies R. We look at the premises and see no mention of R. If you like, R has appeared from thin air. We have only two rules that allow us to introduce statements from thin air. One is the addition rule, and the other is contradictory premises. In this particular proof, we are going to employ the addition rule. However, an alternative proof of the same theorem using contradictory premises is found in a separate video. The proof in that video also uses conditional premises. This version avoids conditional premises. However, unless we do use conditional premises, obtaining an implication such as S implies R may be tricky. To do it, it may be easier to put S implies R into its alternative form using conditional disjunction. Conditional disjunction says that the statement S implies R is the same statement as either S is false or R is true. Since we know nothing about R, recall it came out of thin air, we see that we had better show that S is false. That becomes our first intermediate goal. We need to show that S is false. Now let's look back at our premises. The final premise is the negation of the conjunction of Q and S. That's another one that can be confusing in that form, but we know through the De Morgan equivalence rule that the negation of the conjunction of Q and S could be thought of as either Q is false or S is false. At least one of the two must be false. Since our first intermediate goal is showing that S is false, if we had that Q was true, then we would be able to assert that S was false. So, showing Q is true becomes our second intermediate goal. Remember, since we are arguing backwards, this second goal should actually be achieved prior to the first intermediate goal we discovered. To show Q is true, we look at our first two premises and ask ourselves, can we conclude Q is true from them? We see that either Q or P is true from the first premise, but that P is false from the second premise, so that it is obvious that Q must be true. Our intermediate goal of showing Q is true is easy to obtain, and then from that, the other intermediate goal, showing S is false, is also easy to get. Since S must be false, conditional disjunction could be applied to get our conclusion. So, having finished our strategy, let's see if we can construct a proof. We will first write down the three premises. Q or P, not P, together with the negation of the conjunction of Q and S. From the first two premises, we see that Q must be true, since at least one of Q or P is true, and P is false, so the disjunctive syllogism rule applied to lines 1 and 2 results in Q. Applying the De Morgan equivalence rule to line 3, we rewrite it in the form not Q or not S. Since Q is true from line 4, and we know that at least one of Q or S must be false, then that says that were we to apply disjunctive syllogism again, that we would have S must be false from line 5. We apply disjunctive syllogism one more time to lines 4 and 5 to get line 6 that S is false. Now, using addition on line 6, we introduce R, and yes, R is coming from thin air. However, we know from the definition of implies that if the antecedent, in this case S, of an implication is false, we may say that false antecedent implies any consequence at all. This takes 2 steps, however. First, we use addition on line 6 to assert either S is false or R is true, and then using conditional disjunction, we rewrite not S or R in the form S implies R. And that is the conclusion we sought.